Hi. In this section, we are going to discuss about the concept of Poisson process and how we can define a Poisson process and some problems uh, which can be addressed using the concept of Poisson process. So we start with uh, the concept of uh, counting process. Counting process. Okay, anyhow, before moving into the concepts, we suppose that you are already familiar with the concept of Markov process or the concept of random process and analysis of Markov process and random process. Their parameters like the autocorrelation function, uh, covariance function, etc. All these functions, all these terms, I think they are familiar to you. Otherwise, I recommend you to go through the corresponding sessions before uh, moving into the concept of Poisson process. So now we start with the concept of counting process. A process, a random process x of t uh, is said to be a counting process if x of t represents the total number of events occurred in an interval of a time interval 0 t. That is, as the total number of occurrence in a time interval 0 t. So if you observe the timeline, then this is the number of occurrence from 0 to a particular time point t. As the time point varies, the number of occurrences is also varying randomly, and that's the process. And uh, mathematically, by definition, uh, it should satisfy or it must satisfy some conditions. Like first one, x of t is always greater than or equal to 0 with x of 0 is equal to 0. So at the beginning of time, that is when t is equal to 0, there is no occurrence of the event and the counting starts from 0. That is x of 0 is equal to 0. And at any point of time, the number of occurrence is always positive. Then this is the first condition, and the second condition is that x of t is always an integer, or it takes x of t is an integer, and by the first condition it is a positive integer. And second one, or third one, this x of t is a monotonic non-decreasing uh, process. It is non-decreasing. That is, uh, at time t, if the value of x of t is say something like say n, then at a point say s, which is greater than s, the value of x of t is say m, then this m is greater than n. Or if m occurrence happened in the interval 0 t, then in the interval 0 s, there should be more than n, uh, more than or equal to n events, and that is why we term it as a non-decreasing function. And uh, another uh, condition is that x of t minus x of s is nothing but is the number of occurrence in interval st. Here s is less than t, So x of t minus x of s give the number of occurrence in the time interval st. So these are the four important properties of um, accounting process. Now, in real life example or real life situations, we can have a number of counting examples like say the number of requests to a particular web page uh, at a server, or number of telephone calls arrived at a particular say communication switchboard, or the number of particles emitted from a radioactive substance, or the say the number of customers arrived in a particular queue. All these are some kind of counting process. uh, Now we are going to define the Poisson process. Poisson process. Poisson is name of a mathematician, so we write P in caps, and it's a counting process. Poisson process. X of t be a counting process, and it is said to be, or x of t is said to be a Poisson process. X of t is a Poisson process if it satisfies three or four axioms, which is known as Poisson postulates. If it satisfies the Poisson postulates, which are given by first one, x of 0 is equal to 0. Obviously, it is a condition which is true for all counting processes. Then second one, x of t has independent and stationary increments. X of t has independent and stationary increments. These terms are already defined. Then the third one, probability that um, x of t plus delta t, x of t plus delta t, so like this, x of t plus delta t minus x of t is equal to 1 equal to lambda into delta t plus order of delta t. And another condition, probability that x of t plus delta t greater than or equal to 2 is equal to order of delta t. So the first two conditions are very straightforward. X of 0 is equal to 0 and x of t is independent, and it has independent and stationary increments. And the third condition says that x of t plus delta t minus x of t, that is the number of occurrences in a time interval of size delta t. Delta t is the difference between x of t and t plus delta t and t, and these are the two time points. And x of t plus delta t minus x of t is the number of occurrences in the time gap delta t, and we are looking for the probability that the number of occurrences in small time interval delta t is equal to lambda into delta t plus order of delta t. Order of delta t means it's the powers of delta t, something like delta t square, delta t cube, delta t raised to 4, 5, 6, etc. And the importance of this particular term is that as the value of delta t tends to 0, order of delta t tends to 0. And lambda into delta t is the only term which remains, and this order of delta t tends to 0 as delta t tends to 0. Okay, that's the peculiarity of this order of delta t. It contains powers of delta t, higher powers of delta t. And in similar way, probability that x of t plus delta t minus, okay, this is not x, this is x of t plus delta t minus x of t greater than or equal to 2. There are more than 2 arrivals in the time interval of delta t is order of delta t. So actually, if we look at these two postulates together, the property is nothing but probability that one arrival in a time interval of delta t is given by lambda into delta t, and probability that more than one arrivals in delta t interval is almost equal to 0. So that means in a small interval of uh, length delta t, we have either a 1 occurrence or a 0 occurrence. That's the two different possibilities. So in other words, if you have a counting process, and if we can find out a delta t which is small as we wish, uh, such that in the time interval of delta t there is either one occurrence or 0 occurrence can happen. Such a delta t can be calculated for such a process. So that's the meaning of the last two axioms or postulates. And if a counting process satisfies these four conditions, then we call it as a Poisson process. So that's the concept of Poisson process. Now, for a Poisson process, the most important result which we have is uh, probability that x of t is equal to x of t is equal to say n is given by e raised minus lambda t into lambda t raised n divided by n factorial, where this n take values 0, 1, 2, 3, etc. So that's the most important property of a Poisson process. Um, if you observe the system for a time length of t, then the number of occurrences uh, in that interval 0 to t follows a Poisson distribution. So this is a Poisson distribution. Is a Poisson distribution with parameter or with mean lambda t. So the probability density function of a Poisson distribution with the mean lambda is e raised to minus lambda, lambda raised to x by x factorial. And here we have a Poisson distribution with the parameter lambda t. So if lambda is the number of arrivals per unit time in particular uh, system, then the number of arrivals in a time period t will follow a Poisson distribution with the parameter lambda t. So that's the main or first result which we have about a Poisson process. Another results which we can have about a Poisson process x of t is that the autocovariance function uh, is given by lambda into minimum of t1 t2. The autocorrelation function r x x t1 t2 is then given by lambda into minimum of t1 t2 uh, plus lambda square into t1 t2. So these are another two important results with about a Poisson process. So if we have a Poisson process x of t with average arrival or number of arrivals per unit time is lambda, then the mean of the Poisson process is uh, lambda t, and the autocorrelation function is lambda into minimum of t1 t2 plus lambda square into t1 t2, and the autocovariance function cxx t1 t2 is lambda into minimum of t1 t2. These are another two important results regarding a Poisson process. Now, another uh, important property of the Poisson process is memoryless property. So, since this Poisson process has memoryless property, we can say that this Poisson process is a Markov process. So this is a Markov process. And anyhow, it is not a it's a continuous type of process, and thus we can find out the transition probability matrix for this particular process because it is continuous, but it is a Markov process. Now another important result is that the inter-arrival time of a Poisson process with the average arrival rate lambda is or it has an exponential distribution with the mean 1 by lambda. That means if we count the number of arrivals per time interval t, it follows a Poisson distribution. And if we count the number of arrivals and if we count the gap between two successive arrivals, that will follow an exponential distribution with the mean 1 by lambda. And so the exponential distribution with the mean 1 by lambda is given by lambda e raised to minus lambda t with t greater than 0 and lambda greater than 0. So here we can associate two probability density functions with a Poisson process. One is uh, if you observe the system from time t is equal to 0 uh, to any particular time point, say t, or for an interval of time t, then the number of arrivals has a probability density function which is given by the Poisson distribution, and is e raised to minus lambda t raised n by n factorial, n is equal to 0, 1, 2, 3, etc. So this is the number of arrivals, and if we observe the time gap between two successive arrivals, if an arrival takes place here and the second arrival takes place here, then this is the time gap between two successive arrivals. And uh, what's the time between the current arrival and the next expected arrival somewhere here, and this is a random variable, and that particular random variable follows an exponential distribution e raised to lambda e raised to minus lambda t with t greater than or equal to 0 or greater than 0 and lambda greater than 0. So it is the inter-arrival time between two successive arrivals. So that will follow an exponential distribution. These are the two important distributions which we can relate to a Poisson distribution. Sorry, Poisson process. Now, to illustrate the Poisson process, let us have uh, a few examples. Let's consider a simple one. Um, in a particular computer database, the rate of queries per minute is 6 uh, per 6 per minute. So in a computer database, here you have a database, and queries to this particular database is 6 per minute. And an experiment consists of monitoring the database for, say, m minutes. We observe this for m minutes and record the number of queries per m minute. Then we have x to calculate the number of queries in a 1 minute time interval. Number of queries in 1 minute. Then second, exactly 6 queries. Exactly 6 queries in 1 minute, and 3 less than 3 queries in half-minute interval. These are the things which we have to find out. Anyway, the situation is arrival situation. The number of the questions or queries arrive to our database, and this satisfy all our postulates for Poisson process. You can check it one by one, and since it satisfy all the conditions, it's a Poisson process. Uh, it's a Poisson process. And since it is a Poisson process, you can attach the probability distributions, Poisson distribution and exponential distribution to it. Anyway, here the average number of arrivals per unit time is 6. So lambda is equal to 6. And we observe, in the first case, we observe the system for 1 minute. So the number of arrivals per 1 minute follow a Poisson distribution with the parameter lambda into 1. So the probability density function here is not f of x. We can write it as f of n, or we can write it as probability, we count it as number. So probability that number of customers arrived in 1 minute is equal to, say, small n, is given by lambda e raised minus lambda n divided by n factorial, and the number of arrivals in 1 minute can be vary from 0, 1, 2 up to infinity. Now, the first question, number of queries in 1 minute. So sorry, number of queries in 1 minute has an average value of 6. Okay, it is not number of queries. No. Okay. it is not number of queries, not an abbreviation, it is no queries. No queries means we are looking for the probability that number of arrivals in a unit time, a minute is equal to 0. That is 6 into e raised to 0 divided by 0 factorial. Uh, sorry, Poisson distribution. E raised to minus lambda. Here it is Poisson distribution is uh, e raised to minus lambda, lambda raised to n by n factorial. Sorry. So the uh, required probability here is, let me check the Poisson distribution written over here. It is right. E raised to minus lambda t, the lambda t raised n by n factorial. That's right. Okay. So sorry for the wrong substitution. So here it is e raised to minus 6, 6 raised to 0 by 0 factorial, which is e raised to minus 6. So that's the Poisson uh, probability. We can find this e raised to minus 6 and it is 0.0025 something. So that's the record probability that there is no queries in a unit time interval. Then the second question is exactly 6 queries in 1 minute interval. That is, in the second case, we are looking for the probability that number of arrivals in 1 minute is equal to exactly 6. So that can be obtained by just substituting n is equal to 6 in the expression, that is e raised to minus lambda, lambda raised to n, that is 6 divided by 6 factorial, is equal to e raised to minus 6, oh, then 6 raised to 6 divided by 6 factorial. You have to evaluate it, and using your calculators you can evaluate the value, and it is approximately is equal to 1.1606. And in the third case, we are looking for the probability that number of customers arrived in a half minute period is equal to or it is less than or equal to or less than 3. So uh, to address this problem, uh, the probability that number of customers in a time interval of zero point 0.5, that is half minute, is equal to n is given by is a Poisson distribution with the parameter lambda t. In the previous case t is equal to 1, here t is equal to 0.5. So it is the lambda t is equal to 6 into 0.5, that is 3. So it is 3 e raised it is e raised minus lambda t, lambda t raised n by n factorial. And here we are looking for the probability that n at 0.5, so the number of arrivals in half a minute is less than or equal to or less than 3, is given by number of arrivals in that particular half interval is 0 plus 1 plus 2, and this is given by e raised minus 3. Okay, that's a constant for all the probabilities, so it is e raised minus 3, 3 raised 0 by 0 factorial plus 3 raised 1 by 1 factorial plus 3 raised 2 by 2 factorial can be simplified as e raised to minus 3 into 1 plus 3 plus 3 square, that is 9 by 2. Simplifying it, you will get an approximate probability that 0.4232. So that is how we use Poisson distribution in Poisson process and to calculate the related probabilities. Now, let us have one more illustrative example. Uh, if customers arrive at a counter, we have a counter, and the customers arrive to this particular counter with a Poisson process with mean 2 customers per minute. Customers arrive to this counter 2 per minute, and we had to find the probability that um, the inter-arrival time or the interval between two consecutive arrivals is first one more than 1 minute, second one between 1 and 2 minutes, between 1 and 2 minutes, and the third one less than or equal to uh, 4 minutes. So it is less than or equal to 4 minutes. So in this particular system, customers arrive to the counter in the rate 2 per minute. That is lambda is equal to 2. The parameter of a Poisson distribution. And if you count the number of customers per say for an interval of time length t, it will follow a Poisson distribution with the parameter lambda t. But here we are not going to find out the probability of probability that n number of customers arrive in the system for a time of t. But here we are asked to find the probability that um, the inter-arrival time is more than 1 minute. That is, if we let t be the inter-arrival time, which is a random variable, and then we know that the inter-arrival time has an exponential distribution with the parameter 1 by lambda, with the mean 1 by lambda. So the mean inter-arrival time is 1 by lambda is equal to 1 by 2. That's the mean inter-arrival time. Anyway, the probability distribution is lambda e raised to minus lambda t, t greater than 0. So this is the probability density function which we have to use. And using this, we can find the probability that the inter-arrival time is more than 1 minute. Or in the second case, the probability that the inter-arrival time is in between 1 and 2 minutes. Or in the third case, the inter-arrival time is less than 4 minutes. All this can be calculated using the exponential distribution. But number one thing, exponential distribution is not a discrete one, it is a continuous distribution. So probability that t greater than 1, inter-arrival time t greater than 1 can be calculated as integral 1 to infinity lambda e raised to minus lambda t, that is 2 into t in this particular case. So here also lambda is equal to 2. Is equal to 2. So 2 e raised to minus 2 into t dt is equal to 2 is a constant. E raised to minus 2t, the integral is e raised to minus 2t divided by minus 2 in between 1 and infinity, which is equal to 2 and 2 get cancelled, minus 1 is there, then upper limit e raised to minus infinity, e raised to minus infinity is 0, then the lower limit 1, e raised to minus 2. So the required probability is minus or minus become plus e raised to minus 2. That's the required probability that t is greater than 1. And in the second case, we are looking for the probability that 1 less than t less than 2. It can also given by integral 1 to 2 2 e raised to minus 2 minus 2t dt. It's equal to uh, 2 into e raised to minus 2 divided by minus 2 in between 1 and 2. This 2 and 2 get cancelled and we have a minus. Then the upper bound is here. The upper bound is e raised to minus 4. The lower bound is e raised to minus 2. So the answer is e raised to minus 2 minus e raised to minus 4. And it is approximately equal to 1.117, sorry, 0.1170, etc. And the third required probability is probability that t is less than 4, and anyway t is always positive, so it is in between 0 and 4, which is equal to, here also the integral is e raised to minus 2t divided by, okay, this be the integral from, we can obtain it from here, and in between 0 and 4. So it is equal to minus e raised to minus 4, then plus e raised to 0. Or in other words, it is 1 minus e raised to minus 4, which is approximately equal to 0.9997. So this is how we calculate the inter-arrival time for a Poisson process. So for a Poisson process, the main two things we need to calculate is the probability that number of arrivals in a time interval t is equal to n. This is given by Poisson distribution with the parameter lambda t. And second thing, the inter-arrival time, the time gap between two consequent arrivals. This is say this is equal to t is nonsense because it's a continuous type distribution. So it is something greater than t, or t less than t, or the inter-arrival time is in between some t1 or t2 or something like that. This inter-arrival time is given by exponential distribution with the mean 1 by lambda. 1 by lambda is the mean of the exponential distribution, or the distribution is lambda e raised to minus lambda t. This is the exponential distribution. And the Poisson distribution is e raised to minus lambda t raised to n by n factorial. Lambda t raised n by n factorial. This is the Poisson distribution attached with Poisson process. So the Poisson process is very much important, and it has a lot of applications in data communication, communication systems, signals, and the level of analysis of signals, etc. So be familiar with the concept of Poisson process, and this may have a lot of applications in engineering problems. So be familiar with these concepts. So thank you for the time being. In our next class, next session, we will discuss about the central limit theorem. Okay, thank you.